Okay, now we've been doing modular arithmetic with large numbers. If you see the examples here, for instance, 74x is congruent to 9 mod 13, or this one here, 246x plus 200 is congruent to 401 mod 81. And what we've been trying to emphasize is that whenever you have large numbers in modular arithmetic, you can always reduce those large numbers to a number smaller than the modulus. So in other words, when you're dealing with mod n, you never need to deal with any numbers bigger than n. Now we're going to focus on the numbers from 0 to n minus 1 as a new number system. Now we've already talked about this as Zn. The numbers from 0 to n minus 1 are known as Zn. And we're going to do arithmetic in Zn. We're going to consider Zn as an arithmetic system, self-contained, without reference to other integers. Okay, so in order to do this, we know that we can add two numbers, but we want our arithmetic in Zn to be self-contained. So we want to add two numbers in Zn and get another number in Zn. So basically, what you do this is you add the two numbers x and y, which are in Zn. To get another number in Zn, you have to take the remainder. Okay, so we're going to define a new operation here, which I'll just call circle plus. That if I have x and y that are both in Zn, then x circle plus y is the remainder of x plus y mod n. So that means that if x and y are in n, r is in n as well. So we have an operation defined in Zn. Okay, we'll do the same thing with multiplication. If we have two numbers x and y in Zn, we'll take their product, then take the remainder mod n, and we get a result also in Zn. So we have circle plus and circle dot, and these are our two new operations in Zn. Okay, now we have to prove some consistency about these operations. Okay, so what is this proposition saying? What it's saying is that if I have any two integers a and c, and I add them, and I take the result mod n, that's the same thing as taking b in Zn that's equivalent to a, and d in Zn that's equivalent to c, and adding those two using circle plus. In other words, my ordinary arithmetic converted to mod n is the same thing as first converting the numbers to mod n and using my circle plus addition. Okay, so this reinforces the idea that we only need to deal with numbers in Zn when we're considering arithmetic mod n. Same thing with the times operation. If I have any two integers and I multiply them, that's the same. Take any two integers, multiply them, take the result mod n. That's the same thing as taking the remainder of a and the remainder of c, which are both in Zn, and using this modular multiplication to get the result. Okay, so we're really reducing all arithmetic operations to operations in Zn on numbers in Zn. Okay, and I'll let you read through this proof. I asked for part B as an exercise. Part A, just try to follow through the steps here. And part B is going to be very similar. All right? So that's this one here, part B. Now, I ask you to do a couple of things with subtraction, and you can certainly follow along very closely with addition, the analogous definition and equivalence proof for subtraction. All right. Now, this exercise says, let's build on what we have already and do more complicated arithmetic operations. So, for instance, we have the sum of three integers. We can do the same arithmetic using Zn. So you certainly want to use the proposition you showed already to prove this. Now, well, I'll just give you a hint, is that you're going to want to apply proposition 43 twice. And you have to figure out how to do that you're going to apply proposition 43 twice to the left-hand side of this. Okay, and you'll do similar stuff for parts B and C. Okay, so in exercise 45 we did combinations of two operations. Clearly we can build up any combination, multiple combinations of these operations. And at the risk of repeating myself, what you're showing is that any operation, if you're considering arithmetic with integers and you only want the result mod n, you can take all of those integers mod n, do the arithmetic mod n. You never have to deal with large integers. You only deal with integers from 0 to n minus 1. Okay, here we have another way of representing what we're doing when we do arithmetic in Zn. Now here's our ordinary number line. Now if we consider the remainders mod 5 of these numbers, then we would get this number line here with repeating 0, 1, 2, 3, 4 pattern. You can match this up. For instance, the remainder of 6 mod 5 is 1. The remainder of minus 5 mod 5 is 0. So you see these remainders repeat like this. Now notice if we did arithmetic on this number line, for instance if we took 2 plus 4, we take 2 plus 4, we get 6, and we get down here to 1. But if you think about it, 2 plus 4, if you do modular arithmetic on 2 plus 4, you're going to get 1. So we could do modular arithmetic by doing ordinary arithmetic on this number line, going down here to see what the result is. And that would give us our result mod 5. Okay. Another way to look at this is to make a addition table. And you can verify that if you do modular addition on the two numbers, then you'll get this result. For instance, 3 plus 4 mod 5, this is addition mod 5, so 3 plus 4 mod 5 is 7 mod 5, which is 2. So here you're getting a table that shows the addition. Notice the interesting patterns here. Look at the diagonals. Okay, very interesting pattern in this table. This is a first example of what's called a Cayley table. Right now, here we have multiplication. We can do the same thing. And notice all the zeros here. So there's kind of a qualitative difference between this table and this table. And this table, in some ways, is like a magic square. Notice that in every row, there's only one of each number, and in every column there's only one of each number. Now that's not true in this table here. Okay. Right. So in this exercise, what you're supposed to do is to use these tables to do this arithmetic. In other words, you reduce the big numbers to small numbers and use the Cayley tables to get your result. Now notice a property of these tables. Here's a table for Z8. What you see from this table is if I take the operation of any two numbers in Z8, I get another number in Z8. Okay, any number from 0 to 7 and do this circle plus on any number from 0 to 7, I get another number from 0 to 7. This property is called closure. I can't add two numbers using this circle plus operation and get a number that's outside of Z8. Now, you may say that's clear for this case. It's clear for Z5. Why is it? Is it true in general? Is it true in general for Zn? Okay, that's something that needs to be proven. Okay, same thing is true for multiplication, and you actually have to prove this closure property. And here's what's called a wordy informal proof. You follow along this idea and see why it's true in general that the addition is closed in Zn and multiplication is closed in Zn. I should say modular addition is closed in Zn and modular multiplication is closed in Zn. Okay, so this proof is supposed to give you the idea. Here's a concise statement in mathematical language. Okay, and let's see. So here's some more exercises to explore the notion of closure. Okay, remember the idea of closure is that if you take any two of these and you operate on them, you get another one. Okay, so look at these for these different operations. For instance, let's think about division with integers. Is it true that if you divide any two integers, you get an integer? Think about that. If it's not true, then the integers are not closed under division. Okay. All right, so let's consider additional operations in Zn. We've talked about plus, we've talked about times. Let's think about how these interact with identities and inverses. Now, remember what an identity is. An identity is an element. Well, basically, here's an example of an identity. It's an element that you operate on any other element, and you get that same element back again. Okay. Here you can see 0 is the ordinary identity for ordinary addition. And in this proposition, it's shown. Let's see. Sorry, I have a little trouble manipulating here. In this proposition, it's shown that 0 is also the additive identity for the modular integers. Okay. Now notice here that you need to check in general that a plus 0 is a. In other words, 0 doesn't change a when you plus it on the right. And you also need to show that 0 plus a is equal to a when you plus with 0 on the left. You have to check both of these. Now you may wonder why. You'll see why later. The general definition of identity means that you have to be able to operate on the right and on the left and receive the same number that you started with. Okay. And you can give a similar proof that one is the multiplicative identity. So it turns out that the additive and multiplicative identities of the integers are also additive and multiplicative identities for the integers mod n. Okay, now notice also that no matter what n is, as long as n is bigger than 1, no matter what n is, 1 and 0 are always in Zn. Okay, so let's consider inverses. Now, if you remember what an inverse is, here's a defining equation for an inverse. The inverse of A is a number such that when you operate on A with that other number, here it's called A prime, I get the identity back again. Think about ordinary addition. The inverse of 7 under ordinary addition is minus 7. Why is that? Because 7 plus minus 7 is 0. And minus 7 plus 7 is 0. So that means that if I take 7 and add it to minus 7, I get the additive identity. So that's what an inverse is. Notice that every element, every integer has its own inverse. And the same is true for modular integers. Any a in Zn will have its own inverse. But what is the inverse going to be? Well, you can't say it's minus a because minus a is not a number between 0 and n minus 1. If a is 3, for instance, and we're looking at Z mod 5, then minus 3 is not in Z5. To find an inverse of 3 in Z5, I need to find a number between 0 and 4 such that I take 3 plus that number, it gives me 0 mod 5. Okay. Now, we can actually show that there are additive inverses for every element of Zn, no matter what n is. Okay, and we show that in 2 stages. First, you need to prove that there's an additive inverse for 0. So you can go ahead and do that. Remember the definition of inverse here. All right, then we want to show the additive inverse for any number that's not 0. This means any number in Zn that's not 0. Okay, so you'll have to show that actually here we spill the beans here, that this is actually the additive inverse of A. And you have to show that in 2 parts. You'll have to show that A prime is in fact a modular number in mod n. And then you have to show also that the circle plus of these 2 numbers is 0. So that establishes that this A prime is the additive inverse of A under modular addition. Okay, so for modular addition, we do have an inverse. So can we do the same thing for multiplication? It turns out that you can't. Read through this and you'll see why not. I'll give you a hint also if you want to look at this multiplication table. Remember that to have a additive inverse, you would have to have something that multiplies 0 and gives you 1. Okay, so I'll leave you with that. You can think about how that shows that there's no multiplicative inverse in Z8. Okay. So where are we? Now, it turns out, interestingly enough, it turns out in some cases that all non-zero elements have multiplicative inverses. That's not true in all Zn. It's true in certain Zn's that have special properties. So here you're going to investigate for which Zn's is it true that all non-zero elements have multiplicative inverses. Okay, let's move on to this section also that talks about arithmetic properties of circle plus and circle dot. These two operations are derived from ordinary addition of integers and ordinary multiplication of integers. However, we can't assume they have the same properties. But it does turn out that circle plus is commutative. You can add in either order. And circle dot is also commutative. Circle plus is associative, and circle dot is also associative. Circle plus and circle dot are distributive. Okay? And the way to prove this is go back to the definition. You can't assume this right away. You have to go back to the definition in terms of plus and ordinary times on ordinary integers. Okay? So this shows you how to do this, how to show commutative for plus. You're going to show commutative for times in a similar way. So the proofs here of these properties are going to be similar to this proof. When you want to do this exercise, take a look at this example, try to follow it along, and apply the same logic to show these other operation properties. Okay, so now we get to kind of a punchline. We've been talking about this set Zn, and we've defined two new operations, circle plus and circle dot. And circle plus in particular has both identity and inverses and closure. Now circle dot turns out not to have inverses, so that kind of knocks that out. We also have that Zn is associative. All right? So this set Zn under this operation circle plus has some very special properties, and these are the special properties here. Closure, has identity, has inverses, and it's associative. Any set that has an operation that has these four properties is called a group. Okay, and that this is important down here. Notice that we did not include commutativity in this list. A group does not have to be commutative. Okay, so this is our introduction to this notion of group that we're going to be dealing with throughout the course. This is an abstract notion, and we'll find out that there are many, many examples of groups, and even there are groups whose elements are not even numbers. So we're going to see an abstraction of this general notion of group. All right, now we've shown that modular addition always defines a group. In this exercise, you're going to investigate whether or not modular multiplication ever defines a group. Okay, so we'll end here.